Right. Hi everyone. So um, yeah, in this video, let's discuss about the parameter estimation, which should be the next step of studying probability and statistics in this course. Right. Of course, first we studied probability, up to joint probability distribution. Then after that, we continue to study how to use the concept that's been used in studying probability to apply this to the statistics. And yeah, I think in our last class we studied how to do data description, how to display a description of the data in a good way, and also we learn on how to do sampling process, meaning that if we have a certain sampling, certain samples, what are the probability of the population, right? And now, or what are probability distribution of the population? And now we'll continue on the to study the parameter estimation. This is yeah, as the name suggests, we are going to estimate some parameters. What parameters? They are parameters of the population. And what we mean by estimating is we have the sample, right? We have the sample, and then we have the population. Population, of course, is commonly unknown. We cannot get the data of all of the population. Rather, we get the data of some of the samples, right? Um, and yeah, as this text says, uses sample data to compute a number that is, in some sense, a reasonable value or guess of the true mean, which is called the point estimate. Okay, let me turn off the camera. All right. So these are several notations used throughout these slides. Parameter is commonly denoted as theta. So parameter here, there are several parameters that could be analyzed, but I think for now we are going to focus on the mean and the variance of the sample, as well as the mean of the variance of the population. So sample size is n, and then the expected value, of course, if you have the expected value of x, e of x is the integral of x times fx, right, dx, which is, yeah, the mean. So, okay, so let's start. So a point estimate of some population parameter theta here is a single numerical value of a statistic theta hat. So statistic here is denoted by theta hat. And then there is a point estimate, which is the theta hat, also theta hat. But this one is a capital theta hat, capital theta. Here we use the small theta. And the statistic is called the point estimator, or theta. So maybe I should change the slide a little bit. Let me do that. Okay. So the statistic theta hat is called the point estimator, and the expected value of theta hat, large theta hat, with large theta, is E, E large theta hat. And here we basically compare between theta and the theta hat, right? So the theta hat, large theta hat, again, is the statistic, or it is a numerical value, um, or some measure on the uh, sample that could approximate what happens in the population. So whatever in the population is denoted by this theta, and we want this to be the same, right? So it's called unbiased estimator if these are the same. But if they are not, then there exists a bias, which is the difference between E large theta hat minus theta. Okay. And x bar and s square, they are random variables. So x bar, of course, is the mean, right? Mean of the sample, whereas s square is the variance of the sample. So this is the mean. This is the variance of the sample. Okay. Now, yeah, for bias and unbiased estimator, it's argued that an estimator should be close in some sense to the true value of the unknown parameter. So the unbiased estimator here, E theta hat, again is equal to theta, and there may not be a unique unbiased estimator. So unbiased estimator, there are many of them, or there could be many of them. There may not be one unique estimator, right? And one example of an unbiased estimator is the sample variance, E of S square, so expected value of the S square, right? S square again, here, this is the variance of the sample, okay? So this is sample variance. Now, several characteristics of the point estimator. Here we can see in the slide. So an estimator should be close in some sense to the true value of the unknown parameter. Again, that's the principle that we have to adhere, that yeah, if you want to estimate some value, it may not be, exactly the same, but it should be somewhere close, right? It should not be some value that's very far. And there is MVUE. This is the unbiased estimator with the minimum variance. So this should be the standard of the estimator. So we usually want the estimator to have relatively low variance, right? And we want the estimator to be unbiased as well. And yeah, there could be some estimator that's both of them, let's say both of them, or maybe if you consider like three unbiased estimator, three of them are unbiased, but of course there is only one, that has a minimum value of the out of those three estimators. So that one is the MVUE. And the standard error of the estimator, theta hat, is its standard deviation, which is given by sigma theta hat, which is the square root of phi theta hat, phi of theta hat. Phi is the variance, and the standard error of the mean is s over square root of n. And if the standard error involves unknown parameter that can be estimated, substitution of those standard error, of those sigma, it could actually be changed, or it could be replaced by the estimated standard error sigma hat of theta hat, right? So if you want to estimate the error of the mean, then just replace this this sigma into sigma hat and so on. Now, one simple example here is that suppose we have this data, yeah, 41.6, 41.48, and so on and so on. We can get the value of standard deviation and the value of the square root of n, the population. So population, sorry, the sample. Number of sample here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10, and we have the standard deviation. You can, of course, compute the variance, and then you can get the standard deviation. And the sigma hat of x bar here is 0.08 0.98, which means that this is the standard error of the estimated of a standard error of the mean. So sigma hat x bar, this is the estimated standard error for the mean. Okay, so this is yeah, an example on the argument that okay, actually the standard deviation of or the variance of the population, is like the square of the difference between the current or between the measurement and the average, and then it's divided by let's say n, right? But for this, for the sample, it's actually not divided by n, but it's divided by n minus 1. So this is the one that's shown in the last slide. Okay. All right. So this is the example of the sample variance. So you have the variance of the sample here as square. And what we are trying to do is we will try to solve the expected value of s square, right? So expected value of s square, as you may already now knew about this. So the denominator is n minus 1 instead of n, and then the numerator is the same, xi minus x square. So for the population variance, sigma square, you have the sum of this xi uh, minus x bar square of n, but it's now n minus 1, right? And we pull this out of the expected value operation. So it would be 1 over n minus 1, then multiplied by all of this. And then you have 1 over n minus 1. So try to expand this quadratic. Becomes xi square plus x bar square minus 2x bar xi. And then this turns out to be 0. So now we have this, the sum of the xi square minus nx bar square. So you have x bar square added from 1 to n, which means we multiply this by n. So now we have 1 over n minus 1. Um, then the sum of e, expected value of xi square minus n e, or n expected value of x bar square. Then now we have e as square expected value of the variance. Now, we have this, because expected value of x minus xi square, here it turns out to be expected value of xi square, this is minus x bar square. So this is from the definition of variance. Now you have this being mu, which is the mean, and this is the variance, second moment of this. So x minus xi square here, it is the variance. Thus, exi square is this, right? So it would be mu plus sigma square. and the rest of it will follow. So now you have e for x bar square. Uh, Now you have the similar one. So this would be mu square, but now we have sigma square over n because this is the average of x bar that's used. So now we add this from 1 to n, which means we multiply this by n. And then we multiply this by n also from this. And it turns out to be sigma square. So this means that actually the sample variance with denominator n minus 1, it is, it is the unbiased estimator of the population variance sigma square. So that's why we use n minus 1 and we do not use n. So as you may imagine here, the difference, well, this, for example, will cancel each other, right? So now we have 1 over n minus 1 uh, times n minus 1 sigma square, right? So if this is n, we will not have sigma square. Instead, we will have another value. Yeah, this is from the fact that there is a minus sigma square here from the expected value of x bar square. So yeah, that's how we obtain the unbiasedness of the sample variance. Okay, now on to the next slide. We are going to talk a little bit about the mean square error of an estimator. So for a bias estimator, mean square error or MSE, here it is the expected square difference between theta hat, large theta, capital theta hat, and theta. So yeah, this is the error. So if the estimator is biased, uh, it has an error. But if it's not, then it's it's unbiased. It's said to not have an error because yeah, theta hat and theta here is the same, right? In the case of an unbiased estimate. So it's called MSE, which is an important criterion for comparing two estimators. Yeah, so for example, this is two estimators with expected value of this theta hat being here, the peak, and the real theta is this. So it's indicating that there is a difference, right? The variance difference, and of course the value difference, the bias of the difference, yeah, of the difference between theta hat 1 and theta hat 2. So yeah, that's more like that. Um, Now there are several methods of performing a point estimation. I think there are three, but I think we are going to talk about this only uh, for two methods. So the first one is called the method of moment, which basically we try to substitute or equate the population moments, which are defined in terms of expected values to the corresponding sample moment. So this one, it could produce the unbiased point estimator, and the population moment, the kth population moment is defined as E of the X to the power of K, where K is 1, 2, and so on. And the corresponding K sample moment here is 1 over N, times the sum of xi to the power of k, where k is 1, 2, and so on. And then, yeah, the moment estimators here, theta hat, it's done by equating the first m population moments to the first m sample moments and solving the resulting equations for the unknown parameter. Whereas sample mean here is the moment estimator of population mean. Um, yeah, so now we have this result or this characteristic, and that the moment estimator here is done by equating the first m moments to the first m moments of the sample and population, and we solve the resulting equation for the unknown parameters, right? So for normal distribution here, this is the example that we have mu, the first moment, of course, of this is the uh, x bar, which is the sample mean. So this is the population mean, and this is the sample mean. And we want to find whether this is an unbiased estimator or not by yeah, looking at the two equations here, right? So the first equation again describe the mean, whereas the second equation, so this describe yeah, the relation between the mean and the variance, whether it could be it could be modeled by this by the sum of square of the data of the sample. So we will try to substitute mu here equals x bar, and this is the second one. We try some substitution, which is the yeah, mu now equals x bar. So we try to substitute this into like x bar here, and we try to make the equation now more explicit in terms of sigma square. So sigma square here is the difference between all of this summation, 1 over n, uh, then multiplied by sum of xi square minus mu square. So now we get this divided by n, sum of this minus n times sum of this, or n times mu square. And by substitution, we arrive at the equation here, the variance sigma square is the difference, the square difference of the xi minus x bar divided by n. So this is the variance from this. And yeah, it's concluded that this is not an unbiased estimator. All right, the second method of obtaining the point estimation here is the maximum likelihood, or also called MLE, maximum likelihood estimator. So what this is about is the estimator, this would be the value of the parameter that maximizes the likelihood function. The likelihood function here is L. L theta is the multiplication between f x1 theta, f x2 theta, and so on. And the MLE here is the value of theta that maximizes the likelihood function. So this maximizes likelihood function L theta. And to solve this equation, It would be helpful if we do this using the natural logarithmic or ln. Well, the reason is because the derivative of ln is 1 over x, so that's quite convenient if we want to find, something that requires like rearrangement of the equation so that we get the value of x, for example, for yeah. So if you have like this, uh, so let's see, yeah, the derivative of ln x, right? X for x is 1 over x, right? And for discrete, we can interpretation here. We can say that L theta is the probability that x1, yeah, the one of this x1, fx1 here equals x1, and then x2 here equals x2, small x2, capital X, n equals xn, and so on. There are some properties of the MLE. So the first one is that theta hat, capital theta hat, is an approximately unbiased estimator for theta, and the variance of theta hat, large theta, capital theta, is nearly as small as the variance that could be obtained with any other estimator, and capital theta hat has an approximate normal distribution. So this is the key. There is a characteristic called invariance property, where if you have theta hat 1 to theta hat n, if they are the MLE of the parameters theta 1 to theta n, then the maximum likelihood estimator of any function h theta 1 until theta n of these parameters is the same function h theta hat capital theta hat 1 until capital theta hat n of the estimators theta hat 1 to theta hat n capital. So these are some properties of the MLE. So if we look at some examples here, consider a Poisson distribution with PMF or the probability mass function of fx equals to e to the power of minus lambda times lambda x over x, yeah, x factorial. And we suppose that a random sample is taken from the distribution. What is the MLE of lambda? So what are we doing here? So what we do here is, um, we have population and we have sample, right? So, okay, we have the, um, or previously what we have, if we try to solve the, let's say, some probability distribution, it's given, right? So suppose that you try to find the PMF of this. Well, lambda is given, but how do we find lambda, right? Lambda is the function from the population. That's it's not always the same as with the sample, for example, right? So how do we find lambda so that it's representative of the population? So yeah, one way is by doing this. We find the estimator. We try to estimate some parameters, including lambda here, and it turns out to be yeah, later turns out to be the average of the sample. Okay. Same with other distributions. For example, for exponential distributions, how do we find the parameters? Also lambda, for example. What is lambda, and how does lambda relate to, say, the average or the mean, and probably the variance? So we will find out by doing this estimator, like to try to estimate the mean and the variance by doing this and by performing some methods such as this maximum likelihood or the moment method that we have discussed previously. So yeah, to solve this, we have to know first that the function L lambda here is the multiplication of all of this PMF for the Poisson distribution. Yeah, so we substitute this multiplication. So if you have e to the minus lambda, now the if you multiply this n times, e to the minus lambda times e to the minus lambda times e to the minus lambda, well, that becomes power, right? So e to the minus n lambda, yeah, that's it. Yeah, and then this becomes lambda xi power of xi times lambda to the power of xi times lambda to the power of xi. So we get the summation here, and the denominator here is the same. So it does not really change. We multiply xi factorial n times. So from xi from x1 factorial to x2 factorial and so on. And it's easier to use a natural logarithmic here. Well, again, the reason is because the derivative of 1 is 1 over x, which is a known fact. So, yeah, we try to do learn here. We try to learn everything. So learn L lambda here is if you have like a logarithmic, if you log something that's a multiplication, it becomes a summation, right? If it's a division, it becomes a subtraction. So this would be ln e to the minus n lambda, which is the same as minus m lambda ln e, right? So I think uh, you knew this from high school. Yeah. And then if you have this ln lambda to the power of all of this, so this becomes, it goes to the front, then ln lambda, and we just learn also xi factorial. So now we try to derive this, we try to differentiate this with respect to lambda, because this is a function of lambda, right? So yeah, so you have ln lambda here. So if we try to find the maximum likelihood estimator, which means that we try to find a maximum uh, point here, the derivative here is zero, right? So the derivative of ln L lambda, well, this is zero. This is zero. Yeah, so I will just try to do this. Ln e is 1, right? That's why it's easier to use ln, because can get this fact. We can simplify this equation quite quickly. So we differentiate with respect to lambda, so this becomes minus n. And then we have this ln lambda. Now this becomes sum of xi, and the derivative of ln is 1 over x, so this would be lambda like this, right? And because this does not contain lambda, then the derivative of this is 0. So we have this, and then we have, yeah, n equals sigma xi over lambda, and lambda is sigma xi over n. That's it. right? And that's x bar. Okay, so that's the average. So lambda hat, the estimate of lambda here is just the average for the Poisson distribution, right? So this is the same as the mean of the Poisson distribution, which is the lambda. Right? The variance of the Poisson distribution, in fact, is also lambda. So yeah, you can find this with other way here. Now the second or the fourth example, rather. Yeah, we have four examples. So it's the second example. This is the fourth. Let x be exponentially distributed with parameter lambda. The likelihood function is this. This is the PDF of exponential distribution, and yeah, with the same method, the same way, we can obtain ln L lambda here is n n times ln lambda minus lambda. Um, yeah, we try to again perform the natural logarithmic here. Okay. Yeah, so um, it's like ln lambda to the power of n. Uh, yeah, it's basically like plus like this, right? E to the power of minus um lambda sigma xi. So this is n ln lambda plus now this becomes minus lambda sigma xi times ln e. So ln e is 1. So we just get rid of this and yeah, uh, and so on, right? We basically have this is ln uh, L, and if we derive everything here, this becomes 0. So this is 0, and you have n over lambda, and now you get rid of lambda here, so it becomes sigma xi, and so on. Now you have lambda hat is 1 over x bar. So this is from the exponential distribution of the random variable, the continuous random variable. Now we solve here that if we don't know lambda, so we can estimate well lambda hat, or the estimation. A good estimation here is 1 over x bar. So dividing 1 by the mean. So that's about the maximum likelihood estimator. All right, so the next topic here is the sampling distribution of means. So this is mainly concerning about the sampling, like if we have population, we take sample from the population. There is actually some interesting characteristic of the sample, right? So the probability distribution of the sample, actually it follows certain like rules, certain natural phenomenon, which might be a little bit different from the population. So yeah, basically the statistical inference here, the key is we make a decision about the population based on the information contained in a random sample. So yeah, the goal is to uh, analyze the population, but what we know is the sample, right? So sample distribution here is the probability distribution of the statistic or of the parameter that we have solved before. Um, okay, wait a minute. All right, so probability distribution of x bar here is called the sampling distribution of the mean. So again, probability distribution of X bar. So X bar has its own probability distribution. You know, this kind of concept, we need to study the concept of probability distribution that we have studied before with the probability part. And by reproductive property of normal distribution, the sample mean X bar here, the again, this is not the random variable, but this is the mean. So the probability, the random variable is the mean. X bar. So we have the sample mean X bar. It has a normal distribution with mean mu X bar equals to mu, and the variance here is sigma square X bar equals to sigma square over n. Right. So this is the mean, and this is the variance, and the main result of this very important theorem is called the central limit theorem. So first, if we are sampling from a population that has an unknown probability distribution, the sampling distribution of the sample mean will still be approximately normal. So again, the sampling distribution of the sample mean will still be approximately normal with mean mu and the variance sigma square over n if the sample size is large. So we need a certain sample size to ensure that the sample mean is approximately normal. Okay, so it's a little bit arbitrary, but yeah, it has some scientific reason behind that. So the central limit theorem says that if we have the random variables of the samples, let's say sample x1, x2 to xn, yeah, a random sample of size small n taken from a population with mean mu and the finite variance sigma square. So now we know the population, the mean population and the variance population. Suppose that we know that. And then for sample mean, the limiting form of the distribution is the standard normal distribution with z. Uh, it's like this. It's the same as if you convert from the non-standard normal distribution into the standard normal distribution. We'll have x bar minus mu over sigma over square root of n. So it has a standard normal distribution that way. All right, so one example, actually there are two examples of this. So an electronic company it manufactures resistors that have a mean resistance of 100 ohms and the standard deviation of 10 ohms. The distribution of the resistance is normal distribution, and we find the probability that the random sample of 25 resistors. So we have 25 resistors with or will have an average resistance less than 95 ohms. So there are several data here. So this is the population mean. Sorry, population mean is here. This is the population standard deviation. So this would be sigma, and this would be the mean, which is yeah, mu, right? And we have n, small n is 25. We'll have an average resistance less than 95 ohms. Yeah, so we have all of the data, and this is based on this formula here that the mean and the variance is the mean is okay. The variance is sigma square over n. So the standard deviation here is sigma over square root of n, which happens to be 2. So now from that, if you have like a 25 sample here, that sample will have more or less a normal distribution. And then we can find, we can find the sample uh, yeah, probability distribution of the sample already. Even if we haven't touched the sample yet, we haven't even we haven't, yeah, we haven't even knew what kind of sample that we will have, but we can actually, you know, uh, predict or approximate what the sample would be, what the parameter of the sample. So this is done by solving standard normal distribution. Here you have sigma, yeah, x bar here equals to 2, and this z is obtained by this. So this is the mean. The mean is yeah, 95, and this is the population mean is 100, and this is 2 sigma over square root of n. So just solve this. Z is minus 2.5, and we solve for x bar uh, less than 95, which means we solve for z less than minus 2.5, which is 0.0062. So that's yeah, that's the probability that if we have bunch of what is this resistors, we take 25 of them, we actually know that those 25 will have probability or will have an average resistance. The probability that it will have an average resistance less than 95 is 0.0062, which is very small, right? So we can um, conclude or infer something from the or something on the sample by also knowing what happens in the population. Okay, so the last example here, we have a log normal distribution. If we take 25, or sorry, 20 samples, will the sample form a normal distribution? So this is the log normal distribution for the population. But if we actually take some sample, let's say like a 20 or 25, turns out that it follows the normal distribution. So that's, yeah, an interesting fact. Yeah, actually, I put this from the textbook. If you have, or if you do the sampling with like, uh, let's say, with 20 samples, let's say 100 times, then most of them will follow a normal distribution. Right. So that's I find that interesting. Yeah. So if you have this um, population, you try to take a sample, it would be like something like this. Yeah, so it's closer to the normal distribution compared to the log normal one that we have in the population. So it does not mean that the population is normal. It means that the sample follows normal one, but the population is still the log normal distribution. So that's that's a difference between what happens in the sample and what happens in the population, right? So this yeah, maybe take some time maybe to read the slide of the textbook and to try to get some understanding of this method of point estimation. Okay, so yeah, I think that's all from me in this video. Make sure that you work on the exercise found in the myITS classroom to uh, yeah, for your attendance. So yeah, we will meet again in the class next Monday. I will see you there, and yeah, have a nice day. Thank you.